Now in this example we have now two substances in a cuvette, and we want to measure the two concentrations of these substances at the same time, and we can use that by using different wavelengths if the substances have different extinction coefficients for these wavelengths. So what does that look like? We have a cuvette and we've got substance X in here, and we've got also substance Y in it here, that is substance Y, and we measure the absorbance at two different wavelengths. So here absorbance 1, and we might have absorbance wavelength 2, that would be absorbance 2, and we would get different absorbances depending on the concentrations of the substances. But how can we actually work with that? Of course, we can use the Beer-Lambert law. The absorbance of a substance equals the concentration times the extinction coefficient times the path length, which I denote here with an L, and in our case it's always 1 centimeter. So how can we set this up? Now I've already indicated here with highlighter what the different extinction coefficients for the substances are. So if we look at the substance at the measurement at 423 nanometers, we can write the absorbance at 423 nanometers equals the concentration of the substance X, and I denote this just simply by X, times the extinction coefficient of X at 423 nanometers. So that would be this extinction coefficient here. So times 1857. I'm not writing the units here. We just keep those in mind for later on. And we don't write the path length here because we know it's 1 centimeter. So that is the contribution of substance X to the absorbance, and we also have the concentration of the substance Y, and again we look at the extinction coefficient for the substance Y, which we've got given here, times 1001. And the absorbance was for 423, 0.499. Now for the absorbance at 666 nanometers, we can write something similar. We have X, the concentration of X, and this time we are looking at the extinction coefficient for X for 666, that's the blue one, so times 2498. 2498. Again, I don't write the units, we deal with these units later. And the path length, we again have that as 1 centimeter, and we don't need to write that. Equals 1 times plus 1 plus Y, that's the concentration of Y, times the extinction coefficient for Y, and that is 2934. And that gives us an absorbance of 0.89. 0.879. Now what we have here is really a system of two equations with two unknowns, X and Y. So we need to solve a system with simultaneous equations, which we have written out here, and we really need to find x and y for this system so that the equations are true. Now, we can use different ways of dealing with simultaneous equations. So we could, for example, use the substitution method, we could use an elimination method, or we can use the matrix method, and I want to focus on the latter one, on the matrix method. And I've got another video which I put in the description. I'll put the link to it in the description, how in general the matrix method actually works for a simple system like that. We can calculate x that would be given by the determinant of the x matrix divided by the general determinant, and y would be the determinant of the y matrix, again divided by the general determinant. Now, what am I talking about? We can write these two expressions, these two equations, in matrix form, and we would write it as 1857 1001, and here we've got 2498 and 2934, and that would be our first matrix, x, y, and this would give us the results matrix, which is 0.499 and 0.879. So that's our matrix, and we can now determine the general determinant, so D, and for the general determinant we would take this value times this value, so this would be 1857 times 2934 minus this value times this value minus 1001 times 2498. And if we put that into a calculator, our general determinant would be 2947940. So that's the general determinant which we are going to use for x and y. Now we need to figure out what the x is, and for the determinant of the x value, what we do is we replace the x values that we have here in this column here with the results matrix values. So we would have, for the x, we would have 0.499. The y value stays the same, 1001, and we've got 0.879, and again the y value stays the same with 2934, and we can just simply do the determinant of this matrix. So that would be 0.499 times 2934. So we do this multiplied by that, minus 1001 times 0.879. And when we calculate that, again with a calculator, we would get 584 times 1.8, 584.187. So that's our dx. For the y, we do a similar thing, but this time we leave the x values and replace the y values with the results matrix. So we would get 1857 and 2498. And now we replace the y values with the results 0.499 and 0.879. So that's our determinant of the y matrix, and we would do the calculation again. 1857 times 0.879 minus 0.499 times 2498. And if we place that into a calculator, we would get 385.801. So that's our dy. And now we can calculate our value for x. So x, as I said, would be determinant of x divided by the general determinant. And we can put in the numbers. So we've got for dx, we had 584.186 divided by what we got for d. That was 29,479.40. And if we do the calculation for that, we got 1.98 times 10 to the minus 4. And of course, we then would need to think about what the units are. We had the extinction coefficients in the form of per molar and centimeter to the minus 1, and the length we had centimeters, so the centimeters would cancel each other out, and therefore the concentration would be in the form of molar. And we could write this therefore as 198 micromolar. Probably should make this negative sign a little bit stronger. Now for the y value, we can do the same here, dy over d, and we plug in the number that we just calculated for the determinant of y. That would be 385.801 divided by the determinant 294.7940. And again, if we put that into a calculator, we would get roughly 1.31 times 10 to the minus 4 molar, which we can write as 131 micromolar. So these would be the concentrations of the two substances. X would have a concentration of 198 micromolar and Y would have a concentration of 131 micromolar. And that is how you can actually solve a question like that with the matrix method. You can use other methods, substitution or elimination method, but I find this, especially when the numbers are a little bit not so nice, I find this method actually quite useful and helpful, because it's not a lot of calculations that you have to do with that. So I hope this makes sense, and thank you very much for watching.